My name is Yuri Lebedev. I'm president of Sensorix LLC. Our company is developing a quantum gyroscope, and with this slide, I just wanted to show you the current state of gyro technology. This chart is kind of a linear distribution of different technologies, and on the right side, you can see MEMS technology. That's a very low swap gyros, mass-produced, but they all have pretty low accuracy. And on another side, you have mechanical gyros that are still, to this day, it's an old technology, but to this day, it's hard to beat the accuracy, but it's very expensive and quite large in size. Mostly it's used for strategic and space application. What we're trying to do is kind of break that status quo and develop a quantum sensor that would be highly stable and sensitive, and would be priced reasonably, but at the same time have a very low swap as well. So our mission is to develop a microchip form factor quantum gyroscope using NV centers and diamond technology. This technology, besides rotation, can be used to measure electrical field, magnetic field, temperature, pressure, acceleration. And recently we discovered that a team from MIT together with Air Force Research Lab and Army Research Lab are working on the atomic clock using NV centers in diamond technology with better than 10 to minus 13 frequency instability. So it's a pretty accurate clock, also using the same tech. In the center of the slide, you can see 5 microchip in a small box. This is actually the form factor of the gyroscope sensor element that we want to achieve. And the picture on the right, in fact, is the same chip, but under microscope. That chip was designed for magnetometry. It has microwave circuits, microwave antenna. It has a photodiode and optical filters. In order for us to adapt similar design for our purpose, we need to develop RF circuits, RF antenna. We'll have to find, and it's very important, find a chip scale light source, 520 nanometers wavelength and about 100 milliwatt power. And all of that we need to package with the chip controller, FPGA most likely, and put it in a small package, smaller than or close to MEMS gyros. So how the sensor works. As I mentioned, we're using negatively charged nitrogen vacuum system diamond as our sensing element. You're probably aware that the nuclear has the mechanical spin, and we're in fact using this mechanical spin as a natural gyroscope. And so in order for us to use it within our sensor, just like any quantum sensor, we need to first prepare the quantum state of both electron and nuclear. And we're doing it using laser, microwave, and RF pulses. We prepared both electron and nitrogen nuclear state. Then we apply that state to the environment, which is rotation. And because of nuclear spin precession, the spin of the nitrogen nuclear changes slightly. And that change is then reported through electron fluorescence. And you can see on the right side of this slide, this is in fact the prototype gyro. And the red light is in fact fluorescence from the diamond chip. So our technology can be used pretty much in any industry, but we're really focused on the consumer electronics. Especially our focus would be great to get the smartphone applications. There are about 1.5 billion smartphones produced every year. And if we get 10% of that market with the gyro quantum chip, they could generate about $1 billion in sales. But we're not going to stop with the just a gyro, because the same technology can be applied to build the entire INS system on the chip. So it could be a next step So now I'd like to open for questions, but we are interested to talk about funding opportunities, development partnership opportunities, and of course supply chain partnerships, because we do need to identify the light source that we need to make it a reality. Thank you.
You know, in talking with a lot of different companies doing quantum sensing, or companies that are looking to buy quantum sensors, there seems to be some misinformation out there about how, you know, you're talking really chip scale solution here, and you know, so I think the audience would appreciate, you know, how much is actually going to be on the chip, you know, because this is a very small package.
And I think Alexei can answer, but we're looking at like a sandwich chip. So this one is the quantum control chip that controls, or basically prepares the quantum state. It also the chip that contains the photo diode for readout purpose. Okay, so currently this chip again contains microwave circuit and microwave antenna, so we need to add RF circuits and RF antenna to it. Of course, we'll have to have a power control and FPGA control. So this is not, it will not be the same form factor as you see inside the box. It will be just a little larger, but it won't be, it will be very similar to MEMS device.
Wow.
Is entire assembly, yeah.
Wow. Well, thank you for that. And so besides the you know, the cell phone market, what other markets do you think that you could have once you have this solution available? What other markets do you think are the most promising?
Well, of course, the small UAV applications. Our device, we don't intend to beat, let's say, if I go to this chart, we don't intend to beat mechanical gyros or, for example, laser gyros. And there are, of course, new quantum technology that are being developed, like cold atom gyros. There's NMR gyros. They also will be probably better than from stability and sensitivity than us, but would definitely be much better than MEMS sensors, and therefore they can be used on pretty much any industrial applications. It's again UAVs, car navigation systems, the agricultural navigation systems, of course for various small applications for the warfighter as well.
Yeah, thank you. And then there's we had time for one more question. You know, what is the from Scott Davis? He's asking, you know, what is the line width frequency stability requirement for your light source?
That's Alexei's question.
Not really much. So central wavelength should be around somewhere 520 nanometers. Line width should, you know, like plus minus several nanometers is fine. Stability, intensity stability should be all good, because that's something we care about.
So what's the approximate line width that you need?
Oh, line width is some nanometers.
Okay, nanometers. Okay, nanometers.
Yeah,
I didn't know that. Thank you.